Hi, my name is Amir. I'm studying a PhD on explainability at KTH Royal Institute of Technology. Today, I want to talk about spectral properties of gradient-based explanation methods, which is our paper recently accepted to ECCV2024. Some of the general research questions that are important in explainability are as follows. What is the definition for explanation? How explanations can be evaluated, or how to make explanations less subjective? Well, gradient-based explanation methods means that we assume gradient is a way to inspect the model and understand its inner workings. Besides these questions, we can also ask why gradient of neural networks are sparse, or what causes the inconsistencies in explanations, or why, if I add small noise to the input, I get different signs of the gradient. Here, f shows a neural network, and nabla is its gradient with respect to its input. In this paper, we assume that our input x is a random variable that follows a certain distribution. Let's call it Gaussian. This means our explanation is also a random variable, which is denoted by e in this slide. This view to explanations helps us unify several explanation methods that are based on gradient and perturbing the input of a neural network, although it's not the central focus of this work. Then we find a spectral representation for explanations by roughly taking Fourier transform of gradient of the neural networks. It's important to note that this analysis is being done in an extremely small neighborhood around an image. So it cannot be generalized to all images or a dataset, but it helps us understand the behavior of neural networks in a very small neighborhood around one image. Not only that, but also it helps us understand and mathematically analyze our observations. Intuitively, we can summarize our contribution in one slide. Let's say f is our neural network, and it can be decomposed into several frequencies, which can be thought of as its Fourier transform. If we take the gradient of f, we get a very jittery function that is shown in the second column. As can be seen, a gradient of the neural network kind of amplifies the effect of high-frequency components of f. This means when we naively take the gradient of a neural network and visualize it, we see a sparse activation pattern, which is the result of high-frequency features dominating the gradient at a few pixels. This method is called vanilla grad and usually appears as a baseline in the literature. To mitigate the effect of amplification of high frequencies, researchers have figured out that if we perturb the input data, we can remove the contributions of high-frequency components. Interestingly, this is a very basic operation in mathematics called convolution. For simplicity, we have visualized the perturbation distribution as a rectangular pulse instead of a Gaussian. This is equivalent to taking the expected value of the gradient of a neural network in the neighborhood that is like a rectangular pulse. As can be seen, this can be even reproduced in one dimension to use noise to remove high-frequency components of a function. In signal processing terms, one can say gradient is a high-pass filter and convolving this noise is a low-pass filter. Therefore, their combined spectral effect creates a band-pass filter. This means many explanation methods that do gradient and then perturbation of the input can be seen as band-pass filters on the gradient space of a neural network. Therefore, this is us who decide which frequencies should be removed and which frequencies should be kept. With this spectral representation, it will be easy to show that gradient amplifies the effect of high-frequency features in neural network. Also, we can show that perturbation removes the attribution of those high-frequency features. Furthermore, we can show that sign of gradient actually depends on the chosen perturbation distribution. This means that the sign of gradient is not reliable, and its positive value cannot be necessarily interpreted as positive nor negative contribution to the prediction. As you may know, some have reported gradient squared as a better choice for explainability compared to gradient. With this spectral representation, we can actually show that using gradient squared leads to a simpler form that is easier to use. Finally, we can formalize and justify the inconsistencies we have in explanations, also known as Rashomon effect. We have also included this slide to show how our work fits into the explainability literature. So to summarize, we start with a probabilistic interpretation or representation for gradient of neural networks. Also, we assume that gradient is a tool to understand neural networks better. It's important to acknowledge that there is not a formal definition for explanations yet, and we have several methods to explain a neural network. So we focus only on methods that are using gradient and perturbation. With this view, we can have a unified representation for many explanation methods. And the core of our method is based on finding a spectral representation for explanations. These slides will be available under the caption, and the papers numbered here are available in the reference section. And if you enjoyed this video, please share it and consider reading the original paper for a more formal discussion on this topic. Thank you for your attention. Please let me know what you think in the comment section or feel free to reach out via email.